SPH4C College Prep Physics, looking at examples of mechanical advantage, working with mechanical advantage. Excuse me. And this one is more of a, this first example is more of a static equilibrium example. It's asking, what is the effort force required to hold a 3 kilogram turtle in your hand? And imagine you knew these pieces of data that, the distance from your elbow joint to your hand was 35 centimeters. From the elbow joint to the point of connection right here of the bicep is 6 centimeters. And your forearm has a mass of 1.2 kilograms. We'll pretend that it's concentrated in the center. And I want to remind you that unlike holding a turtle that's right out here, clearly concentrated right there, this forearm is, we're pretending it's all through the center. So that does take away from some of the accuracy, but it's the best that we can do. Okay, so let's look at the solution. First of all, because really when you're holding that turtle in your hand, you are holding two different loads. The first load is the turtle, the second load is your arm itself. And that's why we needed to know this information here. Okay? The mass of the forearm. So you've got two loads. One is T for turtle, and one is A for arm. And then you still have your effort. So I identified all these pieces of data as something that I'll end up using in the equation. The distance from the load of the turtle to your fulcrum is 35 centimeters. The distance from your elbow joint to where the bicep connects is your effort distance or arm, and that's DE. And I remember I told you already that I called the mass of the forearm is mass of the load, that's the arm. So there's two loads, and the second load is the turtle, mass load, which is turtle. Okay, so again, I'm looking for not DE, FE. Oh, right, and I want to know the load distance of my arm, since it's concentrated halfway. So here, if I was going to draw, I could say that right here is my second load. Okay, and that's DLA would be located right there, and it's half the distance between your hand and the fulcrum, it said. So that's 0.175 or 35 centimeters divided by 2. Just put it into meters. Okay. Looking at the solution then, the effort torque that I require is the torque from the turtle plus the torque of your arm itself, right? The two torques, the two loads you have to hold. And so my effort torque is going to be equal to the product of the load of the turtle, which is the mass times 9.8, times the distance of the turtle to the fulcrum, which is 0.35, plus the load of the forearm, which is 1.2 kilograms, times 9.8, times the distance of the DLA, the turtle, or sorry, not the turtle, the center of your arm, center of mass, so to speak, to the joint. Okay? And so you work all, you multiply these together, add it all together, and you get this big number. Well, to get FE then, all I have to do is divide this by 0.06, where 0.06 again is DE. It's the distance of where the bicep connects to the joint. Okay? So this is a harder example. I'd call this one of the hardest ones that you would do. It's not as straightforward, and yeah, and it's because you have to take into account the fact that you're holding a turtle and you're holding your arm up. So if you just held just your arm for a period of time, your arm would get tired, right? That's because it has its own mass. Okay, looking at some more examples. These get more into actually finding all these things, right? AMA, IMA, and percent efficiency. So in this first example, I've got a wheelbarrow full of stuff, and so the mass of that load, the whole thing that you have to lift, is 40 kilograms. Your fulcrum is at the front wheel, so the distance from, say, the center, you always just say the center of the mass, that's the best you can do, the center of my mass, of my load, to the fulcrum is 80 centimeters or 0.8 meters, and then the effort is further down, it's the 1.4. Okay, so we're looking for all these things, and the first thing we're looking for is what class of lever it is. And just looking at it from that point of view, what class of lever is it? Where you have the load in the center, right? Effort, load, fulcrum. It will be a second class lever with the load in the middle. I didn't write that down. Let's do that now. Just put that over here. Okay. And then we know we're given FE. We want to find AMA and IMA efficiency. So first of all, looking at AMA. AMA is load divided by effort, forces, and we know our effort force is 280, so that goes on the bottom, right? The load force is the mass of the load times 9.8, so 40 times 9.8 divided by 280, so 1.4. Okay, that's the AMA. Oh yeah, that's just a sec. That was just the classes of levers to compare it. So again, with the load in the center, it's a second class lever. IMA for a lever, it's the distance from the effort arm, effort to the fulcrum, and divided by the distance from the load to the fulcrum. So it's just a divide. So it's 1.4. This 1.4 divided by 0.8. So it's 1.75. So ideally, if this thing was perfect, I'd get a mechanical advantage of 1.75. We, in fact, in this case, got 1.4. So it's not quite perfect, as they tend not to be. So when we find efficiency, you take the AMA, which is 1.4, divide it by the IMA, which was 1.75, and multiply it all by 100%, and it's 80% efficient. Okay? So there's an example of a mechanical advantage efficiency on a lever. In our second example, we've got a winch, okay, that was used to lift boats of mass up to 950 kilograms using only a force of 30 newtons. So there's a huge mechanical advantage. But there's a huge gear ratio, see? Look at this. Look at my gear ratio. A ton and just a little bit. Okay? So we know the gear ratio, we know our effort force, and we know our load mass. And so in part A, we just want to find the load. Well, the load is just mass times 9.8, so 9310. That was just a straight multiply. If you'll please pause, okay, because I'll start going too fast. But so load is just mass times 9.8. That's easy. Part B asks us to find AMA. Well, we know the load we figured out in the last part A is 9310. It's big. And our effort is given in the question, effort force of 30 newtons. So it's 30. So our actual mechanical advantage on this rusty old winch is 310. Okay? That's how you find AMA. For a gear, the IMA is just the gear ratio, so 450. Okay? Again, please pause because I'm moving on. And percent efficiency is actual mechanical advantage divided by ideal times 100, so 310 divided by 450, so 69%. Okay? And that actually is about right. Like levers should be more efficient than something like a winch, or because friction would have a much bigger play in how this thing operates than on a lever. Okay, a pulley example. So Bugs has got a pulley system here used to lift his carrot. So his carrot's 250 grams, and he only applies 1.5 newtons to lift it. So again, all these things we have to calculate. So calculating the load is mass times 9.8. The one thing, 250 grams, you have to put it into kilograms, so you divide by 1,000. Okay, so this 0.25, I took the 250 divided by 1,000, multiplied by 9.8, so there's my load force. Okay. The load of the carrot's 2.45. AMA is load over effort, so we know he uses only 1.5 newtons to lift it. So load divided by effort, 2.45 divided by 1.5, or 1.63, is my AMA. And IMA for a pulley is the number of strands pulling up, so in this case 2. And finally, percent efficiency is actual divided by ideal times 100, so 1.63 divided by 2 times 100, or 82% efficient. Okay, and I know that I'm going pretty fast, so you might need to pause. We're going to move on to the next example of an inclined plane. So Ferd here is pushing a dresser, and we know the dresser has a mass of 86 kilograms, up a ramp by applying a force of 450 newtons. And in part A, we need to find the load force to do that. So load force is the mass of the dresser times 9.8. Okay, so it never changes. Start to see the pattern in the questions. The main thing you need to be able to figure out is, how do I know the IMA for a given machine? That's really the hardest part, and that's where you have to probably write it down on your formula sheet. In part B, we need to find the actual mechanical advantage. So we know his effort is 450, and we knew his load from the last part was 842.8. So his actual mechanical advantage is 1.87. IMA on a ramp or an inclined plane is the length of the inclined plane divided by the height of it, like how high the dresser. So the dresser would have started on the ground, ended up in the truck, so we'll call that 1 meter. And the length of this inclined plane is 2.2 meters. So dividing that out, you get an IMA of 2.2. So when finding percent efficiency, there's the question. Determining percent efficiency is AMA divided by IMA, so 85%. So you know you did something backwards if you end up with a number greater than 100. So if you'd accidentally done 2.2 divided by 1.87, well, you must have done something wrong, because that works out to greater than 100%. Okay? But yeah, those are my examples of calculating mechanical advantage and efficiency. And I think that's it. That's all the notes for this unit. And the rest will be just to sort of work on some of the labs and that, and get a better handle on it.